What powers your search results, your bank, your games, and that AI model that finishes your sentence? Not the cloud. Buildings. Yes. Data centers built from steel, copper, and coolant do the heavy lifting behind every click. Vast, humming data centers that are quietly becoming AI factories. Today, we tour data center evolution and reveal how steel, copper, and coolant shape the digital world. A data center is a specialized facility with thousands to hundreds of thousands of servers, storage, and network gear. Think of it as a power plant for computation. Its job? Keep compute available, secure, fast, and cool. 24/7. What are the core functions? Compute. From general CPUs to GPU trays that accelerate AI. Storage, flash, hard drives, and object stores that keep your data at reach. Networking. Leaf-spine fabrics move packets with low latency and massive bandwidth. Power flows at medium voltage inside the building to cut losses. Busways feed rows. PDUs split clean power to every rack. UPS bridges outages. Some sites use flywheels for instant ride-through without battery stress. Cooling plants circulate chilled water to keep silicon in its comfort zone. Air handlers shape cold aisles and capture hot exhaust with precision. In AI halls, a single rack can draw 3,100 plus kilowatts. Liquid cooling makes it possible. Full immersion tanks push even higher densities while keeping acoustics low. Many facilities run on medium voltage distribution inside the building to cut losses. Some experiment with direct-to-rack DC power to reduce conversion waste. Era 1, mainframe rooms 1960s to 1980s, single massive machines, chilled rooms, uptime above all. Era 2, client server, rows of 1U boxes, early hot aisle and cold aisle separation. Era 3, hyperscale, custom servers, containerized builds, leaf-spine networks, and PUE as a scoreboard. Era 4, edge and specialty, close to users for low latency. Underwater pods, desert air, and heat reuse experiments. Era 5, AI factories, liquid cooling, GPU-dense racks, 400G, 800G links, fabrics like InfiniBand, RDMA, NVLink. The bottleneck isn't CPUs anymore. It's power, cooling, and interconnects. White space, racks in rows with cold aisles for intake and hot aisles for exhaust. Racks and trays, how many inches? 19-inch frames, 42 to 60U tall, cable trays above, power below. Busways deliver power. PDUs and branch circuits distribute it safely. Server types, 1U and 2U, blades, JBOD storage, GPU trays, with NVMe over fabrics for flash pools. Cooling, CRAH and KRAC units, rear door heat exchangers, and direct-to-chip liquid for high-density racks. Networks, leaf-spine with optics, multiple availability zones to isolate failures. Sites cluster where power is cheap and reliable, climates are cool, and fiber converges. Think Nordics and the Pacific Northwest, plus hubs near subsea cable landings. Waste heat into neighborhoods, closed-loop seawater cooling, and evaporative systems in deserts. Teams, facilities and mechanical keep chillers, pumps, and water chemistry steady. Electrical teams manage medium voltage gear, UPS, battery or flywheel, and generators. Network and SRE operate routing, fabrics, load balancers, and on-call response. Power arrives in redundant topologies, N+1 or 2N, with hours to days of generator fuel. Fiber enters on diverse paths, tying into dark fiber and backbones. monitoring spans BMS or DCIM, thermal cameras, smart PDUs, and leak sensors end-to-end. Some facilities use flywheel UPS for the first few seconds of an outage. No battery stress, instant ride-through until generators ramp. Google led on PUE tracking, custom servers, and large-scale air economization tuned by data. AWS operates regions with multiple availability zones for fault isolation and rapid capacity turnups. Microsoft explored underwater modules and advanced liquid cooling, backed by renewable power purchase agreements. Meta shares open compute designs and optimizes airflow with Nordic heat reuse. Across hyperscalers, standardized rack envelopes let new generations slot in without re-engineering halls. AI training turns electricity into heat at breathtaking rates. Air alone can't keep up. Direct-to-chip and immersion become mainstream. Network gravity, ultra-low latency fabrics make cables and optics as strategic as GPUs. Supply chain reality, transformers, switchgear, and fiber lead times. Now gate AI capacity. Siting follows watts, water, and wires. These campuses anchor local jobs, bolster grids with demand response, and reuse heat for communities. Google Hamina, Finland, seawater cooling for coastal. Google and Haminan Energia launched an off-site heat recovery project at Hamina that's expected to cover 80% of local district heating demand, alongside the site's signature seawater cooling from the Gulf of Finland. Underwater Pod, Microsoft Project Natick, a two-phase research program to test sealed, lights-out data centers on the seafloor. Phase 1 ran 105 days in 2015 off the U.S. Pacific coast. Phase 2, Northern Isles, put a shipping container-sized pod with 12 racks, 864 servers about 117 feet down near Orkney, Scotland, tied into a 100% renewables local grid. When you say cloud, picture aisles of machines, lakes of coolant, miles of fiber, and megawatts of power. Orchestrated so your app never goes dark. As AI accelerates, these aren't data centers anymore. They're intelligence plants. Now you know, in AI halls, a single rack can draw 30 to 100 plus kilowatts. Liquid cooling makes it possible. They're built like industrial facilities, grid-adjacent substations, GPU pods by the thousand, and fiber trunks feeding non-stop training and inference. You were also excited to know about the projects by tech giants on the data centers. Which project excited you? Microsoft or Google? If this clicked, subscribe for more and drop a comment. Which part of this intelligence plant surprised you most?